I'm live, it says. Hello, hello. Am I live? Maybe. Maybe. It does seem like I am. Oh, let's get, get everything sort of focused in here. Here we go, here we go. Howdy, everybody, which is nobody right at the moment. I'm gonna end up figuring out a kind of a tight way. I end up jumping into this, or maybe I never will because transitions are hard for me. So maybe it will always just be kind of a little wonky, but that's okay. I think the place to start is at the beginning, and for people attending here, I think the way to get the most out of this, your beginning, is to go to .com. Eventually, I'll be able to in the description and stuff. I just need an additional verification that, I need to work through that verification. I've had errors. Anyway, but for now, you'll go to thecalculustutor.com. If you go to thecalculustutor.com, hold on a sec. Let me make sure I'm at thecalculustutor.com. You will. This is the website. This is my website. And you can see the stream. You can access the stream right here. If you want to submit if you want to participate, submit a question, which I highly recommend. That's what this is all about. You can click this Learn More, or the banner that's at the very top of this page right there. You can click that. And then it takes you to the actual dedicated stream page, which again, you can access the stream there. And there's a homework submission form button on it. My hope is that this is what you get. Submit your homework questions below. I allow people to attach images because I feel like that's critical, but in order to do that, this form has to collect you have to be logged into a Google account. If the Google account you're logged into access this is your school one, it may not let you. I'm not sure. Please, anybody who tries, and if they can't, please let me know and I'll figure it out. So my hope is that this is the easiest way to do it. This just walks you through submitting a good question so I can give you a good answer. But let's say you can't access this form or you just don't want to. What you can do, back on my site, instead of clicking this button, you can just email the question directly to me. That doesn't have nice prompts though, so here's how you submit a good question so I can get you a good answer to it. Include your name and your pronouns. This is your problem. So just whatever you prefer there. The problem source is going to be really helpful as we go on. What will help other students who have questions about the same problem or the same class or questions in the same class keep all that stuff together. And that's for me. Then, of course, your question. Be as specific as possible. What part of the problem is giving you trouble? What did you already try, right? If you just send me a picture of your textbook, homework problems, and just say number 8, I can do number 8. I can work through steps, but I won't know what part of it gave you most trouble. And so I won't know what to focus on. I'll have some ideas of common places where students get tripped up, but the more specific you can be in your question about what specifically about the problem is making it hard for you, then the better my answer can be for you. That said, sometimes your question is, the most specific you can be is, I don't know where to start. I wasn't there for this day, or these problems don't seem like the problems we did in class. I don't know where to start on this one. And that's fine. If that's as specific as you can be, that's great. And that will work for me. I'll show you how to get started for sure, or whatever. And then, of course, you can attach images to the email as well, and I hope you do. Attach a clear and complete picture of the math problem. What I mean by that, by clear, that it's legible, that it's not blurry, and that the text is big enough in the picture that it can be read. Because sometimes it looks like it might be readable, but when you go to zoom in to actually read it, it's very blurry. And then a complete picture means take a picture of the entire problem. Don't make sure none of it's cropped out. Try to include any diagrams that are included with the problem. And if there's instructions for the problem, sort of separate from the problem itself, try to include those, right? Because like on a worksheet, the instructions might be at the top, but the problems you need to do, the problem you have a question about is like way at the bottom. And so if I don't know what those instructions are, I may not be helping you with the aspect of the problem that you actually need help with, right? Because absent from the instructions, a math problem can mean all sorts of things, or want you to do all sorts of things. So if you need to take multiple pictures to capture all of that in a clear, complete way, that's totally fine. The form, you can submit up to 5 pictures, which I think would be plenty. Email, you should be able to include basically as many pictures as you want. But that said, don't overdo it, just enough pictures. The other thing, though, that you include a picture of is any work you've already done. If you've got partway into this problem and then got stuck someplace, or maybe you worked all the way through it and got an incorrect answer, and you're not sure how you were supposed to get to the correct answer or why your answer is incorrect. If that's the case, send me a picture of all of your work as well, a clear, complete picture of that. My promise to you, I won't ever show that image of your work on stream without your permission. So if you're cool with me, maybe I should add that to the form. Just a little checkbox. Are you okay with me showing your work on stream? And it'll sort of default to unchecked or default to no. Anyway, which means I also know that means like if you have a worksheet or something and you're trying to take a picture of the problem you want help with, sometimes it's hard to capture that picture without also capturing your work. And just know I'll take care of that on my end. I will make sure, like you might see just a couple of pencil or pen strokes in the image I post of the problem, but nothing to expose your work if that would make you uncomfortable. And if there's just no way to do that with the image you send, I'll just transcribe it. And where will I transcribe it? So once I've received some questions, how are we going to go about interacting, and how am I going to go about answering those questions? Well, I'm glad I asked. By and large, this is probably the view you're going to be that will be most common on this stream. Little image of me, and then a big image of Miro, which is an online collaboration tool. It's like an infinite whiteboard, which is really, really great. And I'm thinking I'll do one Miro file per week. And if you look, the way this is organized is I just have each day in its own separate little column. I have tons of columns here in case like I run over, I suppose. But that was sort of my thinking is as I do problems, I'll just work down. Maybe each problem will be in a separate column. There's all sorts of ways to do this. I'm figuring it out. Anyway, and I need to come up with a way to share this file with all of you. So I can share a link to this file that you can just browse around in. And, I can share it in just read-only mode. In fact, there's a link as a viewer, commenter. See, I can give you comment access. I use this tool with the students I tutor one-on-one, and I give them editor access. So they don't even, and to access this, you shouldn't need to log in to Miro, create an account, anything like that. You should just be able to see it. So if I do that and I copy the board link, so I'm going to open an incognito tab and paste that link. So what you would see when I have a good way to share this link, which eventually will be in the description of the videos. And I'll have a place on the website where you can just click on it, because there'll be a place on the website to get to all the old videos and old notes and stuff like that as well. It is a little slow the first time you load it. I'm doing all the streaming stuff, and I'm loading. It's loading this as if it's loaded it for the first time. So long as you don't like clear your cache and stuff, and you're not in an incognito window, it should load a bit faster when you get back in there. That said, the Thursday stream, the stream at the end of the week, it's going to go slower because it's full. Anyway, so yeah, this is what you would see. And you'd be able to pan around. You can zoom out. You can go and look at all the other stuff that's in there for that week, all the other questions. Notice you can see where my cursor is. So if I'm answering your question, you could follow along and see right where I'm at. You could even, up here, you can click on me, and then it will follow me. So notice, so this screen is now moving, not because I'm moving the screen that I'm sharing, but because I'm moving the screen that I'm actually working on. And you can follow me around. It's really, really cool. I like it. It is the best tool I've found for this. Anyway, so for right now, if I do that, I'm testing this really quick just to make sure this is going to work the way I want it to. Follow along at all right. Yeah, I think this is going to work just fine. And if it doesn't, we'll learn. All right. So follow along at this URL. It looks like it makes it clickable in the chat. That's pretty cool. I'm going to pin this message. Nice. Okay. So this seems like maybe a thing I'll start doing for now is at the beginning of the stream, just pin the Miro board to the top of the chat. That's cool. So yeah, that's how you submit. This is where I'll do the work. Let me check for some submissions. And I mean, after you submit it with the form, Google Forms are usually pretty quick. And I have the back end pulled up, so I should be able to see your submission pretty quick. If you email me, that's a whole other beast. The way I have my email set up, emails are already a little slow to come into me. So if you submit via email, just be patient. It will come in. And my plan is to more or less get to the questions as they arrive to me. So if it feels really important to you, submit your question on the form because it's fast and you can't access it, please let me know. But it looks like no response is there. I don't see anything in my inbox just yet. So we will grab another problem to use is what we're going to do here. I still want to work on some math. At the very least, I want you all to see what's going on. I do have a student. You know what might be a good thing? So I can work on a problem. But when I don't have a specific problem to work on, it's also an opportunity to engage more with like just a topic. And I have a student with whom I'm going to need to talk about. Oh, I need to share my screen again. I closed the window I was sharing. So there we go. And I forgot what I was saying. That's totally okay. Oh, yeah. I have a student. I will be going over like prime factorization. So I say factoring, and there's different. deal with factoring at different points in mathematics as we're teaching it in school. I'm talking specifically about numerical multiplicative factoring. Specifically talking about the idea of a prime factorization. There are, if you want to get good at math, if you want to feel like you're good at math, which I think is actually what most people actually want, whether or not it means they're good at math, because that means so many different things. But people want to feel like they're good at math. And so I think that often means they want to feel like they understand numbers. So there are a few. We stopped teaching understanding of numbers after, I don't know, 4th-ish grade, I think. Sort of depends a little bit, but definitely sort of before you get into middle school, and definitely by the time you've gotten into middle school, we've stopped teaching you to make sense of numbers. We're trying to push to move on and push you towards algebra skills at that point. And we just hope you've gotten all of the number sense, like the core foundational number sense that you need. So what I mean by that is understanding just how the number line and our number system works. One way you can do that, one thing that would make you feel more confident with numbers is if you were good at your count bys. Count by threes, 3, 6, 9, 12, 15, 18, 21, 24, right, 27, 30, so on and so forth. If you feel like you could do pretty much any count bys pretty much forever, then you probably feel like you're good at math. And if you can't, you probably feel like you're bad at math. I haven't done a formal study on this by any means, but that seems true to me in the experience I've had with people struggling to learn math. And my experience with people who feel like they do understand math. So one of the things you can do all on your own to get better at math is just practice your count bys. And it's a thing you don't need any tools to do. Maybe when you're first starting out, you actually literally write out a list of your count bys. So here, I'm going to get rid of this prime factorization thing for just a second. So maybe, especially if you're doing, a count bys that you struggle with, right? Your sevens or something, right? So maybe you write those out initially. I'm going to encourage you to do all of your count bys starting at 1, and then 7, and then 14 and 21. You don't have to, though. 7, 14, 21, 28, 35, 42. And now I'm going really fast because I know these ones, at least out pretty far. But if you didn't, getting from one number to the next might take you a couple seconds, and that's totally fine. That's why you're writing it down. Now you have a list you can look at. And what you're not trying to give yourself like infinite lists of numbers to memorize. That's not the goal here. Your goal is to understand why the list of sevens looks like this, to understand that 7 and 14 and 21 and 28 and 35 and 42 are all fundamentally connected by the fact that they exist on this 7 count bys. This is also your sevens times table, is another way we call it. So this is another way of saying learn your times tables. I think this is a good way to learn your times tables. This is 7 times 1, 7 times 2, 7 times 3, times 4, times 5, times 6. And that's all your count by list is. And if you start, like when you see the number 35, when I see the number 35, I just right there alongside of it, I'm like, oh, well, 35 is 7 times 5. That's 35 has a 7 and a 5 in it. And there's a reason I focused on two numbers that multiply rather than numbers that say add to make it. We'll talk about that in just a second. So yeah, so this is a good exercise you can do that you don't need anything to do. So it can be helpful to write down each list of count bys initially. And I would say don't make your list out 10 numbers. That's too short. Some, especially as you get slightly bigger, going out just 10 numbers won't necessarily show you the full pattern. I would go out at least, we commonly teach students in elementary school, their times tables out to their 12s. I would say push yourself out to 15 or 20. In high school, I learned my times tables out to 15 instead of just stopping at 12, mostly to speed myself up in math class, because I found myself like I was great with everything on the 12 by 12 times table, but as soon as it was like a 13 or a 14 or a 15, I'd have to like hesitate, and I'd inevitably reach my calculator. So I just memorized them out to 15. But it wasn't memorization. It was looking at the patterns. Let me show you, then we'll move on to prime factorization. Let me show you a smaller number than 7 so we can see a pattern emerge more quickly. Let's just look at our 3s, right? So we do 3, 6, 9, 12, 15, 18, 21, 24, 27, 30, okay? And now I'm going to start over just to try to keep so this list doesn't get too long. And, and let me, y'all stop following me. There we go. Just to make sure all the numbers are visible, I'm going to go back up here. 33 now, 36, 39, 42, 45, 48, 51, 50, 51, 54, 57, and now 60. So the next number has to come after 60. Based on this pattern here, what do you think it is? We could count 61, 2, 63. But notice the pattern here. 3, 6, 9, 2, 5, 8, 1, 4, 7, 0. 3, 6, 9, 2, 5, 8, 1, 4, 7, 0. It's the same pattern. It will always be the same pattern. In fact, that's true for every number. There's a pattern to those ones digits. We can continue the 7s out. 49, 56, 63, and now we're at 70. And so I'm going to go back up here. 77, 84, 91, 98, 105, 112, 119, 126, 133, 140, 7418 529 630, 7418 5296 30. Over and over and over again. It doesn't matter what number you're doing. Let's throw this down here. This is another reason I like Miro. I can just very quickly reorganize stuff so that I can say, so here's our theme here. So is your question, so want to get better at math? Is that, oops. If that's our goal, if that's your goal, then here, yeah, so what we're after here, here's my recommendation, is, so the thing you most need to do want to get better at math? Learn how numbers work. And I would say no. I would say math is is understanding already how the numbers work and then using the numbers to accomplish something. which might just be figuring out new mathematics or something like that. So the number system is one of the tools of mathematics. Maybe one of the primary ones. It's the one from which mathematics definitely stems. But this is how you get better at math. You learn how numbers work, not question mark, exclamation point. There we go. So the one way you can do that is practice count bys, right? Count by threes, count by twos. The math word for this, right, is multiples and factors. But it's just your count by lists. It's just being comfortable with your count bys. So this is recommendation number 1, is practice your count bys. You can do this all on your own. And like I said, you don't actually need anything. Maybe write them down initially if you want to, but once you've done that, once you're practicing them, you can just do it in your head while you're standing in line at the grocery store, while you're waiting for class to let out, while you're waiting for class to start, whatever. You can sit there and in 15 seconds, you can go 3, 6, 9, 12, 15, 18, 21, 24, 27, 30, right? And start finding those landmarks in your count bys. Once you get to 30, you might feel some relief because now you're sort of reset and you're like, okay, I'm at 30. So from 30, I can go 33, 36, 39. So it has to be 42, 45, 48, 51, right? And you just go, push yourself further. I want to show you one more count by just to illustrate that. So notice these patterns are really long. In fact, they're 10 long. That's not a coincidence. But not all numbers have patterns like that, right? 5s, 5, 10, 15, 20, 25, 30, right? It just goes 5, 0, 5, 0, 5, 0, 5, 0. You already knew that. Even numbers, 6s, right? We'll go 6, and we'll go 12, and we'll go 18, and we'll go 24, and we'll go 30. And notice we've now started over 6. So I'll start over here, 36, 42, 48, 54, 60. So notice 6s go 6, 2, 8, 4, 0, 6, 2, 8, 4, 0. And that's going to be true of all even numbers. Odd numbers will hit every number on their way through. Well, hold on. Prime numbers, and we'll get to prime numbers. So when I say prime numbers, don't worry terribly about that definition yet. Some numbers will go through every number. So notice on the 7s, there's a 1, a 2, a 3, a 4, a 5, a 6, a 7, an 8, a 9, and then a 0. And same thing for the 3s. Each digit appears once before it recycles back up. Even numbers can't do that because even numbers will never you can't add even numbers together to get an odd number, right? And so even numbers will only go through half of the sequence. They will only go through the even numbers, right? We can see 2, 4, 6, 8, and of course there's 0. So yeah, practice your count bys. I'm pointing out all these different patterns right now. You don't have to recognize them on your own, but just by doing them, you will start to find some patterns that are consistent for you, some parallels between the 7s and the 17s, or the 3s and the 6, 12 is right. So here's 6, 6, 12, 12, 18, 18, 24, 24, 30, 30, 36, 36, 42, 42, right? The 6s are completely contained in this. Why do you think that is? Are there any other numbers that are like that, or is that just a weird 3 6s thing? are there knowable conditions when that will happen, when one number's count bys will be completely contained in some other number's count bys? Do we have a word for that? Right, these are great questions to have, and that's part of the point of doing practice like this, is it leads you to genuine curiosity about the numbers. You can, and now you may not be able to answer that question yourself. You could Google it or ask your math teacher, but you could also come here and ask. The questions you ask here don't have to be math assignments. They don't have to be homework. They can be actual, genuine, real curiosity about math. That would be great. That's going to be the less common thing, because you all have homework that's due on a regular basis, over and over and over again. You always have homework problems to do. So there's going to be more homework problems in your life than genuine math curiosity questions that emerge just because on one versus the other. Okay, so that's practicing your count bys. One really good suggestion for how you can, I'm going to say get, but really what I mean by that is how you can feel better about math. Feel like you are good at math. That's our biggest goal here. Feel like you're good at math. Because you can be. You can feel like you're good at math and then be good at math. Let me check to see if there have been any question submissions. I'm trying to get better at sort of regularly checking. I have been keeping an eye on I'm starting to figure out my setup, keeping an eye on viewers. So that's, you saw I got caught up, right? Like this is not my favorite part of doing this via streaming. And I knew this was going to be the case. This hasn't surprised me, but it's just that there are several other things to pay attention to. There's the chat. There's the sort of the dashboardy thing where you can look at like views and stuff like that. And I need to be aware of that, especially with a low traffic stream, because the things I do when nobody is currently actively watching are going to be different than the things I do when somebody is actively watching. And so I need to know when those people pop in. With a more active stream, if there's always somebody watching, then you're just always in that mode, right? So like right now I have these sort of two modes, which is totally fine. But it doesn't look like any responses via the form. Let's check the email. Let's check our electronic correspondence. Okay, spam, nothing in spam. Okay, well, that's fine with me. Shall we move on to my number 2 recommendation, which is, oh wow. So this one is kind of understanding prime factorization. This is the next step. Once you have your count bys, and you don't have to be confident that you can now do them. Be confident you could choose a new one. Practice enough numbers that you feel that you really believe that you could pick a new number, 17, and you could learn the count bys, right? 17 is a tough one, actually. Like, bigger numbers are tougher. They jump through things. They jump through the number line much faster, right? So the numbers get big quick. So you have 17, 34, 51, 68, 85, 102, like, yeah, it gets big quick. But these patterns still, or, not just these patterns, but other patterns. Anyway, I want you to be confident you could. You don't need to necessarily actually do it. So that said, once you feel comfortable moving at different intervals through the number line, you are now set up to more easily understand the idea of prime factorization. Okay, so the idea here is any whole, we're going to say, any whole number. And actually, we could say integer to be really, really specific. This is true for more than just whole numbers. It's true for integers generally. Actually, no. I forgot I was defining prime numbers. I thought I was defining something else. Any whole number, we'll focus just on whole numbers. Whole positive number. So we're talking about our counting numbers. 1, 2, 3, 4, 5. We're not talking about 2.5. We're not talking about fractions. Just whole positive numbers. So we're not thinking about negative numbers just yet either. So but that still leaves an infinite number of numbers, right? You can count 1, 2, 3, 4, 5, 6, 7. You can count forever. You will never reach a last number. So any whole positive number is either the product of two smaller whole numbers or is prime. So think of any number. This is not the definition of prime factorization. This is sort of a point building up to that. Any whole positive number, so 23, is either the product. What is product? Right? Here we can do. Let's define over here. Remember, product is the result of multiplication. There we go. So these blue notes here, these light blue notes, I try to be pretty consistent. These are things that I'll try to do definitions there, but it's also equations are just ideas that would be good for you to know kind of off the top of your head, or at least, in the notes that you have made yourself, the notes, so these are good notes for you to be aware of. And I try to make them this light blue so they're a consistent color. So as people are scanning through these note documents, it's easy to see these things because these are often going to be the types of things that people are going to try to look up. And if you find one of these, chances are the stuff around it is related to it and provides more information or an example or context. But yeah, so that light blue, those are notes. So a product the result of multiplying two smaller numbers, or it is prime, or it is prime. There we go. Those are the only options for positive whole numbers. So let's give ourselves some examples. Let's do 20. Let's do 22. 22 is equal to 2 times 11. It's equal to 2 other numbers that we can multiply together. What about 23 though? The only 2 whole numbers you can multiply together to get 23 is 1 and 23. It's not the product of 2 smaller whole numbers. It can only be the product of itself, which is not smaller, and 1, which is technically smaller, but it's the 2 smaller numbers is important here. So this tells us that 23 is a prime number. A number that the only numbers you can multiply to make it are just 1 and itself. So we're talking about multiplication as if multiplication is special. And I mean, all the operations do their own thing, but multiplication is, in fact, special. At least it provides a restriction on the number line that is useful to us. Multiplication creates really useful patterns for us to be aware of and make working with numbers potentially easier, or give us more ability to work with them. Whereas other operations, so like for comparison, why don't we care about if a number can be made by adding together 2 smaller numbers? That's because that's always true. Right? With very few exception, like 0 and, well, we're not counting 0, I guess. So 1 can't be made by adding 2 smaller numbers. 1 is the only positive whole number that can't be made. And then literally every other number. And not only that, and this will come when we talk about prime factorization, if you take it doesn't have to be a super big number, just 10, right? 10 can be made by adding 9 and 1, 8 and 2, 7 and 3, 6 and 4, 5 and 5. There's all sorts of different ways to break that down. There isn't one unique way to break it down. And that can be useful, the fact that there's multiple ways and not just a single way. But that means that knowledge about 10, about all the numbers that add together to make it, it's just a lot. And as the numbers get bigger, it gets bigger and bigger and bigger too, right? Like 100 has a ton of different ways, 49 or 50, in fact, to add 2 numbers together to make it. Multiplication is different. So this number 22, a whole bunch of different sets of numbers you can add together to get 22. There is only literally one pair of numbers other than 1 and 22 itself. So that's sort of what makes this one prime. We don't count this because like with addition, for any sufficiently big number, there's always 2 numbers you can add together. This is true for literally every number. Every number is 1 times itself. So this doesn't actually give us any useful information, or it doesn't give us any like exploitable information when we're trying to work with numbers. And so numbers that have that property are like these big like boulders in the number line. You have all of these numbers that you can break up into smaller numbers, and then periodically you have this other number that just stands on its own. We could not have built that number by multiplying any smaller numbers. We had to have gotten there just through the number line. But then now once you're at that point in the number line, now 23, say, is a number that you can use to make bigger numbers. 23 times 2 gives you 56. And in fact, that's the only way to multiply to get 56. So to get to prime factorization, I want to address sort of a kink, a complication in what I just said, or a contradiction, what might seem like a contradiction, right? So what about let's do a number like, let's just do 12. Because it has a few. It's 12. Let's do 24, actually. I want to do 24. It's just a little bit more interesting. What about 24? 24 can equal 1 times 24. But remember, we don't really count that one because it's always true. It could be 2 times 12. But 24 can also equal 3 times 8. It can also equal 4 times 6. And then that's it. Those are all the pairs of numbers. So I went just slightly bigger than 23, and now we're in the same place I said for like 10, right? All different ways to add to make 10, all different ways to multiply to make 24. Here's the thing that makes this different, though. If we now look at our factors, right? And so let's give ourselves some space from these ones. This 12, well, what makes up 12? Well, you can get 12 by multiplying 3 and 4. So this can be 2 times 3 times 4. Well, now there's a third thing. Now I have 3 numbers, though, not just 2. I thought we were talking about pairs of numbers. And we are. We're breaking this down. We found a way to multiply two numbers that weren't both prime. But if we break down the one that isn't prime, this 12, right, we get a 3 and a 4. And we can see this 4, we could also, there's multiple ways to multiply to make 4. It's not a prime number. Well, there's not multiple ways. There's just that one. So the 4 is 2 and 2. So we could write this as 2 times 3 times 2 times 2. Or I'm going to put it in order. 2 times 2 times 2 times 3, just to keep the 2's together, right? So we can see easily how many we have. And now look what we have. We have a set of, these are prime numbers, right? The only numbers you can multiply to get to are 1 and 2. 1 and 2 itself, so it's prime. Same thing with 3. And now we have a list of prime numbers that we multiply to make 24. So here's 1, 2, 3, 4, 5. Well, these two are the same. They're just in different order. So I showed you 5 different ways to multiply to make 24. It starts to maybe feel confusing, but I want to show you something really quick. Stay with me. Let's look at the next one. Let's look at 24 equals 3 times 8. Oh, there's that 3, a prime number, but 8, oops, crossing stuff out here. Move this down. 8, we can get by doing 2 times 4. So we get 3 times 2 times 4. Oh, that's looking familiar. 4 is 2 times 2. And so we get 3 times 2 times 2 times 2. And all the 2's are together. That's the same thing as 2 times 2 times 2 times 3, because we can multiply in any order, right? It doesn't matter what order you multiply a bunch of stuff in if all you're doing is multiplying. Do you think this one breaks down the same way? Look, neither of these are prime. This is the way to break 24 down into 2 non-prime numbers. This is 2 times 2. This is 2 times 3. So this is 2 times 2 times 2 times 3. And check it out. No matter how we initially break 24 down into 2 multipliers, what we would call 2 factors, right? Numbers that divide other numbers are called factors. Let's write that. Factors are, did I underline the other one? I didn't. The numbers that can divide other numbers. Right, so we figured out that 2 and 12 are a factor pair, are factors of 24, but so are 3 and 8, and so are 4 and 6. But then if we keep breaking down, anytime we break it into a factor pair, if either of those numbers aren't prime, if we then break them down into a pair, and we keep doing that until we can't break the numbers down any further because they're all prime, then what we get is the same result no matter what order we go in, which means this is like the prime number recipe, the prime number blueprint for the number 24. 2 times 2 is 4, times 8 times 2 is 8, times 3 is 24. And it doesn't matter what order you multiply these numbers in, like we said, right? We could do 3 times 2 is 6, 2 times 2 is 4, and that's how you get all of these other numbers. These are the prime factorization. You don't need to do, like, see how I did it all 3 ways? You don't need to do it all 3 ways. You just need to get to this result. And notice you can get to it no matter which pair you started with. And that's my point. This right here, this is the only set of numbers you can multiply together, set of prime numbers you could multiply together to make 24. But there's an infinite number, there's not an infinite number, I'm so sorry. But there's a much larger, it's more than one group of numbers you could add together to make 24. Or if you broke them down to their fundamentals, every number is just 1 plus 1 plus 1 plus 1 some number of times. 24 is 1 plus 1. You have 24 ones, you add them all together, you get 24. Every number breaks down that way in terms of addition. In terms of multiplication, every number breaks down into a unique prime factorization that's different from every other number, or is itself prime. If you can't break it down into a prime factorization, it's because it is prime. It would be a prime factor for some larger number still. Every positive whole number is either the product of some group of the prime numbers that came before it, and sometimes they repeat those prime numbers, like 24, you have 3 2s in there being multiplied. And so this is why we care about factorization, is because this is one of the reasons we care about factorization, is it breaks down complicated numbers into their smaller multiplicative pieces. And that might seem like just kind of like a random curiosity that you can do that, but we can actually use it to find information to make working with numbers easier, actually. So that's what prime factorization is. And so practicing doing this is the step here. So I'm actually going to go back up to my little step here, and we'll say, in front of this, we will say practice prime factorizations. Choose a number. You can just start writing down digits. Start with 2-digit numbers. Move on to 3-digit numbers. Write down a 7 and then a 6. 76. Okay. Right. So we're gonna. This is a little example for us. Find the prime factorization of 76. In my head, I just was choosing digits. 7, sit, and then a 6. Sort of makes sense that they would follow each other. So what we do here's our process. 76, we just find literally any 2 numbers that multiply to make it. Now, one of the reasons I recommend doing the count bys first is because they can help with this. It can help you figure out what numbers multiply to make other numbers. For instance, you may have noticed if you did your 2 count bys, and I do recommend do small numbers. Start with small numbers and you do 3s. You may have noticed when you did your 2s that you hit literally every even number along the way. When you do your 2 count bys, you don't miss any even numbers. In fact, the even numbers are sort of defined by that fact. So that means every even number, if this ends in a 6, it's divisible by 2, which means 2 times something equals 76. You don't have to know what that is in your head. You could use a calculator. I happen to know that it's 38, or, I figured it out, but you could do 76 divided by 2. Or and figure out that 2 times 38 is 76. Now, 2 is a prime number, so we don't have to break it down further. But 38, well, it ends in an even number, so it can't be prime because it's divisible by 2. So we'll put a 2 here, which is a prime number. 2 times what is 38? 2 times 19, actually, is 38. And now we want to break down 19. 6 and 3 go into 18. So what about 4s? 4 goes into 16 and then 20. 7 goes into 14 and then 21. 9 goes into 9 and then 18. Yeah, there's nothing that goes into 19. 19 is also prime. And so what you just figured out that 76 is made up by multiplying the prime number 2 times the prime number 2 again times the prime number 19. And that's the only set of prime numbers that you can multiply to make 76. And then also 76 is the only prime number these make when you multiply them, but I feel like that's kind of obvious. Nobody expects when you multiply the same numbers that you would somehow magically get a different result. So there we go. That's your prime factorization. That's how you can practice it on your own. You literally, and then to find out if you got to the right prime factorization, you can just multiply them together. 2 times 2 is 4. 4 times 19, if you're not sure what it is, you can do it on calculator. 4 times 19 is in fact 76. And you can check to see if you're right. I think math that you can practice, you don't need somebody else to make practice problems for you. You don't need somebody to check your work. If your goal is to feel like you're good at math, to be good at math, if that is your goal, to just be comfortable with math, honestly, not be worried about a math class anymore, that sort of thing. If that's your goal, you can work on these on your own. You don't need anybody to make them for you or check them for you or teach you, the right answer, anything like that. You can make you putting random numbers together and then working through this process. You can practice and you can check your answer. And then if you run into issues or something, right, which is inevitable, there's all sorts of things you might run into. You might do a weird number and you're like, this one seems weird and different. Bring it here. That's a great question to ask here. That's an authentic, real math question that stems from your own real curiosity because you're trying to understand the pattern of how the numbers work. And I promise, we're just focusing on the positive real numbers, right? So it seems like there's there's all the negative numbers too, not to mention all the decimals and fractions. And how is this going to help me? All fractions are just a particular way we arrange whole numbers. Decimals, all of this stuff is applicable to decimals actually, and it will help you with that. There's some additional number sense stuff that we can talk about that helps specifically with decimals, because that comes into some place value, which isn't perfectly overlapped with prime factorization stuff. It's a different sort of idea. And an idea we can talk about here. Heck, maybe actually I'll add a third step here. This is kind of a nice little emergent lesson. What are the steps you could take to get better at math? To feel like you're better at math. If you feel like you're better at math, you will be better at math, right? It's not about deluding yourself into just doing affirmations every day. You wake up before you brush your teeth, you look in the mirror and say, I'm good at math, and you don't do anything else. No, but if you're practicing these things, the fact that you're doing the work, for a lot of us, will trigger a thing in our brain. And if you're getting stuck and then asking questions and getting unstuck, if you're getting stuck and finding the answers on your own and getting unstuck, that's just learning. That's just learning. So yeah, the prime factorization stuff can be a little bit harder to do just in your head, especially as the numbers get bigger. There's a lot of sort of parts moving around. So this is something that definitely probably benefits from having like a notebook, at least pencil and paper. Whiteboard, your workplace, you might have a whiteboard in the break room or something where you can sit and work on this during your lunch break. You're sitting there, you have your sandwich in one hand and you're just sort of doodling numbers on the board idly while you're doing it. It can be a very, for some people, it can be kind of a soothing activity, kind of mindless activity. And trying to make a mindless activity of it is a really good way to strip some of the power out of math for yourself. For some people that really do are starting to develop, an aversion to math, or have already developed an aversion or a phobia around math. If you have a phobia around math, I can't imagine you're here. I want this to be a welcoming space, but I just understand the sheer idea of it would not probably sound inviting. If you're starting to develop an aversion to math, you're in the process of developing that aversion, you are giving math a sort of undue power in your life and over you that you can totally dismantle by just doing small things like this and showing yourself that you can. All right. So those are two things you can do on your own for free. You don't need anybody, and they'll make you feel more confident with math, more confident working with numbers, and we can build upon that. If you try some of this stuff, you run into trouble, or you want more examples, you can always come back here. I am always happy to talk about this sort of stuff and answer those sort of authentic, curiosity-driven math questions in addition to math homework questions. All right, so we have practice your count bys. Practice prime factorizations. And down here, why don't we do practice place value. This one, I'm more riffing on this one. We're getting into real improv here. The other two are things I've talked about before. In almost the same way in terms of like practice them, and this is what you can practice. In grad school, we talked a bit about teaching place value. It was part of like a project or an assignment or something, but that we were sort of riffing on that. And then I've definitely, when I was teaching middle school, I definitely had a few lessons where I was, it was clear some of the students didn't have a good grasp of the idea of place value. And so I was like, I tried to come up with a lesson. But what I haven't thought of is how you can do it on your own in a similar way to these previous ones. I do think it's useful, though. This is a big... This could be... So what I mean by place value, it's okay if I don't. Maybe I'll come up with, as we're talking about it, I'll come up with like a good sort of on your own, don't need anything, sort of way that you can practice this. But for now, let's just talk about what I mean by place value. Place value is the position of a digit in a in a number. Right? So this stems from how the sort of fundamentally this idea of place value stems fundamentally from the number system that we use. We use a base 10 number system. This is not the best or the perfect number system, and it's not the only one that humans have ever used. Culturally, there have been base 16 and base 64 number systems. Like, I don't want to speak out of place. I go in and out with my math history, right? If I haven't talked about stuff in a long time, I forget it. But I used to know a little bit more about the history of, but even in modern times, right? So I'm trying to refer back to, like, did Mayans or Aztecs, or did, like, were there like Sumerian mathematicians or something? I don't think so, because we get our numeral. So anyway, culturally different base number systems have been used in different places by different groups of humans through history. Even today, there are a few very, very common number systems that aren't base 10 that get used all the time. One is binary. You've heard of binary. That's sort of the core base computer coding language. There's also hexadecimal, or sometimes just referred to as hex. If you've done any sort of color manipulation on a computer, you've definitely encountered, like, hashtag and then 6 numbers or letters, right? That is actually a base. Hexadecimal means 16. That's a base 16 number. And so what do we mean by a base 10 number, base 2, base 16? What is the base? What is the 10 of this all? So what this means, what a base 10 system is, it's just our number system has 10 unique digit symbols that correspond to the first 10 values. Whole number values, right? So when we start talking about bases, right, it can get very confusing, because oftentimes we still use base 10 in that language even while we're referring to, right? So 10 unique digits, 10 as in the base 10 as in this many, right? And for a lot of this might be how I refer to how many numbers I'm talking about. And so, and you know what these symbols are: 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Those are symbols. Sometimes they get written slightly different ways, but they're just substitutes, right? A 1 sometimes is written this way. A 4 is sometimes written that way. Zeros can be written all sorts of ways, with dots or little lines inside them, that sort of stuff. Nines are sometimes curvy, sometimes they're straight-legged, things like that. So the shape of the symbols can be ever so slightly different. It's like a typeface option, but the value of the system doesn't change. The value of 0 is this many. The value of 1 is this many. The value of 2 is this many. The value of 3 is this many. The value of 4 is this many, right? We could right? Just to complete it, right? I use kind of dice type pips or whatever, just as an illustration to say, we have a symbol that directly represents a value, a concrete agreed upon value, and that's key here. And this is it. Any number we write uses these and only these digits. And when the digit is used, it always represents what's the way to say this? It always, so if we write the digit 8, it always in some way represents this many things. Now, what those things are can change. And so here's what I mean. Base 10 number system. So here's an example. Right, so if we have the number 2, 5, 7, right? This 7, well, that represents 7 things. That's just a 7. This 5, look where it's at. It doesn't represent a 5. What does it represent? It represents 50. So what does it represent 5 of? It represents 5 10s. Okay. What about this 2? That 2 doesn't actually represent 1, 2 things. It doesn't represent this many. Look where it's at in the number. What does it represent? It represents 200. Which is, so 2 of what? 2 of these hundreds, right? A thing that's worth 100. And so notice what this is. And then 100 is 10 squared, 10 times 10. And if we added another digit, we put a 3 out here, that would be 3,000. 3 times 1,000, 1,000 is 10 to the third, right? And so these are each place values. This right here, right? This is the hundreds place value. This is the tens. This is the ones, right? So we can say hundreds. Oh, wow, that is very sloppy. Oh, I can zoom in more, though. Hundreds. Tens. Ones, right? And then after that would be thousands, 10,000s, hundreds, thousands, millions, 10 millions, 100 millions. And it goes forever. We have an infinite number of place values. The numbers just keep getting bigger and bigger, but we only have 10 digits to use to represent them. So what happens is we run through them all in order. Once you've gotten to 9, the next number, what we call 10, well, that's just going back to the beginning to 0, and then adding a 1 out in front that now it's 1 what? It's 110. It's how many times you've gone through the number line, or not through the number line, through the available digits. You know, these place values are essentially just trackers. How many times, if you're counting, how many times would you have to go through the digits to get here? You'd have to get to this. Well, this 2 says that you'd have to go through them 2 groups of 10 times. Or rather, 20 groups of 10 times. The 5 says you'd have to go through 5 times, and then the 7 says you have to go partially through all the way up to 7. One more time. Don't go all the way through. So this is what I mean by place value. How can you practice this? I think a big thing is kind of just, as you notice numbers out in the world, picking them apart and just going through this and saying, what is that number there? You know, you see a big number that says, 3,852 or something like that. And you're like, okay, the 3 there represents 3,000. And this might feel basic, like this might feel like kindergarten or first grade stuff, right? And it kind of is. That is where you start learning about this stuff. But I think the mistake some people make is they assume that you also stop learning it there, or that it stops being useful there. And it's not. It's fundamental to the number system. And I think oftentimes kids don't really master it at that young age, because why would they? But we don't re-emphasize it heavily enough to help them remaster it when it would be super helpful as they're going into middle school and then as they're going into high school mathematics. My headband keeps falling off. I want to keep thinking about this one, about how do you practice making like working with a base 10 number system. I mean, I think just being aware of it, thinking about it periodically is just like, man, we just have 10 symbols that we use, and that makes all of the numbers, and literally all of the numbers. It makes all the fractions and makes all the decimals, because what's a decimal? Ooh, so these are place values. Actually, we can label this. These are what we call the place values. We name them, right? And it just tells you how many whats is a digit there worth. A 2 here is 200, is worth 200s. That's what the digit is telling you. The value of the digit is that many of these things. Let's look at a decimal, because that's relevant here. Here's another example. Let's do 91. Oh, actually, I'm going to do 90.31. There we go. And the decimals can keep going this way. We have more and more numbers following the decimal, just like we have bigger and bigger numbers here. So as we go up this way, the thing that the digit represents, what it's the value of, is a thing that is itself getting bigger and bigger. This is, oops, I already have nothing. This is 9 times 10. This is 90, right? 9 times 10 is what that 9 represents. And then the 0 tells us we have 0 ones, right? So that's how you get a number like 90, is you just have a 9 in the tens place, and then no ones. You've gone all the way through the digits exactly 9 times, right? You've gone 0 through 9, 0 through 9, 0 through 9, and you've gotten back to 0, but have not continued on. After that 9th time, boom. Okay, so notice as we move to the left from the decimal place, as we move this way, the place value represents bigger and bigger values, multiples of 100 every time, right? This is tens is times 10, hundreds is times 100, but 100 is just 10 times 10, 1,000 is 10 times 10 times 10. So each place value, because remember, every time you go through it, it takes 10 digits to go through. So every time this goes back to 0, that's an additional 10. And we're keeping track of the tens here. And then this is keeping track of how many times we've gone through the tens, basically, right? Each digit tells you how many times the digit before it has cycled through completely, how many complete times it cycled through. It's like the mileage gauge on your car, right? The portion of miles tick up, and only once it gets all the way around does the next one tick up. So that's what's going on here. So if this is ones and this is tens, then this right here is tenths with a TH. Tenths. This right here is hundredths. And now as we're going to the right, so notice, as we move to the right along the number, we get to smaller representations. If we start at the 2 and move to the right, we go from hundreds to tens, tens to ones. And that pattern continues here. Tenths are smaller than ones. In fact, they are exactly 1/10. This is 0. Oops. This is 0 times 1. This right here is 3 times 0.1, or 1/10. This 1 represents 1 times 0.01. 1/100th. If you, like, a penny is 100th of a dollar. So how do you represent a penny in terms of dollars? 0.01. A dime, you need 10 dimes to make a dollar. So a dime is 0.1. This is a dime. 0.10, you could do that. Any decimals, or sorry, I said decimals, any zeros past the last non-zero digit, either to the right or to the left, those are just what we call placeholders. Those are there to represent, to hold the space for that place value, even though there isn't any actual value there, right? So just like that, this 90 right here, this we couldn't write 90, the actual number, not 90. We couldn't just get rid of that 0 and just have it be 9.31. That's a very different number than 90.31. So we need, even though there are no ones here, we put this 0 here to hold the place for them, because we know if we add 1 to this, there needs to be a place to put that 1. If we add 2 or whatever. It's the same thing with these other zeros here. This 0 we can't get rid of, but I can optionally put a 0 here. I don't have to, and I could take it away and it doesn't change anything, because this 0 is past, as we move to the left, the last non-zero digit. Optionally, here, I'm going to write this like that. I could also write a 0 here. This 0 also isn't doing anything. It's sort of just holding, it's holding the place of the thousandths. This is holding the place of the hundreds with a D. But if you get rid of it, it doesn't change anything. You still, this 1 still represents 1/100th, or how many of these smaller ones you have. So we talked about moving to the right. If we move to the left, it's the same thing as up here. It's 10 times, right? So how do we increase this number? By making this number go up to 2, 3, 4, 5, 6, 7, 8, 9. Once we get to 9, this number will go up and then return to a 0. And then we have to increase this number by 1 to say this digit has increased, has gone all the way around 1 more time. So we increase this digit. Now this one's at 4. This one goes up to 5, 6, 7, 8, 9. Once this one's at 9, if we need to increase it again, it returns back to 0. But because it went all the way around again, we have to increment this one. So this would become a 91. And this could be a 1 or a 2 or a 3 all the way up. And once that hits 9, then we'd return it back to a 0 and then increase this one, because now this digit has gone all the way through all of its digits once. So we have to keep track of that here. But this is already a 9. So when we go to increase this one, because this went all the way around, this one goes up to a 0. And we have to keep track of the fact that this went all the way around once. So where do we keep track of that? We keep track of it right here in the hundreds. As I mentioned, there isn't a great thing necessarily to practice on your own with this. I'm going to keep thinking about it. I really love the idea of sort of foundational math practice that people can do on their own. So practice place value, understand place value might be a better phrase for that. Practice your prime factorizations. How do bigger numbers break down into smaller numbers that would multiply to make them, and how far can you break that down? You should be able to break it down all the way down until every number in the list is prime, and then what you have is called the prime factorization. And then of course your count bys. This is start here. Don't worry about the other two until you really feel like you've mastered a few of your count bys, to where you feel like, okay, I understand how 3s work. I could go forever with 3s. I understand how no matter what number I'm at, I could get to the next number. with my 3s without really having to think about it, like do it on your fingers or whatever, right? If you feel like that, move on to your 4s. Or if you feel like you really feel like you understand the small numbers, move on to a weird, slightly bigger number. Do your 13s. 13s are weird. 13, 26, 39, and then jump up to 52, 65, 78, but then jump up to 91, 104. Anyway, challenge yourself. You will be able to challenge yourself at kind of just the right level. Oftentimes, especially when you're sort of doing this in your head, find those places where you get stuck and then think about why you got stuck. Bring that question here. We can talk about it. Or maybe you didn't get stuck. Maybe you realize something that feels either weird or is counterintuitive, right? Like you feel like you discovered something that you didn't think could be true, or that like goes against something you thought you learned in school. Things like that. Genuine, curiosity-driven math questions, because you're just exploring how the numbers work. Neat. This was a neat little diversion of a session. I do want to emphasize, that it's not just homework problems, or even just these genuine curiosity-driven math questions. Maybe there's a topic you've been covering in class, and yeah, you have homework problems, but you don't even feel like you're at the place yet where you can tackle them because you just don't even feel like you understand the topic. And you would like me to talk, kind of like this, do a mini lesson, about that topic. I'm more than happy to, for factoring polynomials. That's another thing related to this, but sort of algebraically, it's sort of the algebraic version of that. Completing the square, or graphing quadratics, or the unit circle. Anything that, if it would just be you think it would be useful to hear somebody else talk about it, and you could be in the chat asking questions, right, getting clarification, directing me. You're like, could you talk more about this part of it? That sort of stuff. So I hope so. I hope that's what happens. I hope this was useful. If somebody ends up watching this and decides they're going to practice their count bys, that would be amazing. This is it. This is the end of my first week of Homework Help streaming. Anybody who stopped by live, nobody asked any questions this week, which I totally expected. I have had a few people pop in. I don't think I've had ever more than one concurrent viewer, which is totally fine. Again, first week. Kind of a bit of a soft launch in a way. Next week, so I'll be back Sunday at 11. I'll do 11 to 1 again. I really like that as my Sunday time. And then next week, I think I'm going to push back the Monday through Thursday hours just a little bit. I'm going to do 3:30 to 5 next week. And I think I'll update the website kind of right now. I think that'll be better. I had ideas for why 3 o'clock made sense initially, but now that I'm in it, I'm realizing I don't think it makes as much sense as I thought it did. And starting at 3:30, when school actually lets out, feels like it makes a bit more sense. Some students are going to be able to do this from school after school, which I think is great. And so they'll be able to jump in right around 3:30, right? And then some of those students who might be able to have gotten out of class a little earlier or whatever, they'll be able to just jump into the stream like right away as it's starting. My hope is that those students might already be waiting, and that would be excellent. Maybe their questions already submitted. And then we can jump right in at 3:30. Students that need to go home first, my hope is that gives students enough time to get home and still have an hour, 45 minutes of time to log in and ask and get their questions answered. I'll continue to adjust. We'll see what happens. Give me feedback, though. Email me, whatever. Let me know if you think there's a preferred time. I'm also going to, not next week, maybe the week after, I'm going to start experimenting with some like more late night times, streams that might start at 8 or 9 or 10 p.m. because I feel like that could be useful to students as well. All right. That's it, though. I hope you all have an excellent Friday and then an awesome weekend. And I'll be back right here on Sunday. Have an awesome day.